So, good evening. Today, I am going to discuss the two-way layout with equal number of observation per cell. I am going to discuss the two-way layout. Equal number of observation in the cell. Let Yijk be the kth observation in the ij cell, where I from 1 to p, j from 1 to k. That means there are two factors, A and B. A has P levels and B has Q levels. And each level combination contain n number of observations. So k from 1 to n. The yes, told me good evening. The model appropriate for this type of data is following fixed effect. Fixed effect model. That is Yijk, which is equal to mu plus alpha I beta j plus gamma ij plus Eij. Eijk follow IID normal 0 sigma square for I from 1 to P, j from 1 to Q, k from 1 to n. And obviously n greater than 1. Okay. So here alpha is the fixed effect of ith level of A, beta j is the fixed effect of jth level of P, gamma ij is the interaction effect of the two factors. Interaction effect of ith level of A and jth level of B. Now least square estimator and SS. SS means sum of squares. We know least square estimators obtained by minimizing L, where L defined as Eij k square, where Eijk is Yijk minus mu minus alpha I beta j minus gamma j whole square. Okay. With respect to mu alpha I beta j gamma ij. Then the normal equations are partial derivative with respect to mu Yijk minus mu alpha I minus beta j minus gamma ij. This is equal to 0. This means I from 1 to P, j from 1 to Q, k from 1 to M, Yijk equal to PQM mu plus QM sum over I from 1 to P alpha I PM sum over j from 1 to Q beta j M double summation I from 1 to P j from 1 to Q gamma ij. Okay. I denote this by equation number 1. Similarly, partial derivative with respect to alpha I, this gives j from 1 to Q, k from 1 to M, Yij k QM mu plus QM mu QM alpha I plus M j from 1 to Q beta j plus M summation j from 1 to q gamma I. I denote this by equation number 2. Then partial derivative with respect to beta j equal to 0 gives I from 1 to p, k from 1 to m, yi j k, q pm mu m sum over alpha I from 1 to p mq beta j pm mu. This is mp. This mp. Okay. mp beta j in I from 1 to p gamma I j. I denote this by equation number 3. Partial derivative real with respect to gamma I j equal to 0 provided summation k from 1 to n yi j k m mu m alpha I m beta j plus summation this is m gamma I j. I denote this by equation number 4. So if we add the equation for I from 1 to p in 4, we get the equations in 3. Please check it. Similarly, if we add the equation in 4 for j from 1 to q, we get the equation in 2. Again, if we add the equations in 4 for all ij, we get equation in 1. Hence, the last set, that is equation 4 of PQ equation, is the only set of linearly independent. Linearly independent equation. The number of unknown quantities that is number of alpha, that is mu, which is alpha is that means plus p, beta j that means plus q, and gamma ij, this gives pq. So number of unknown quantities pq plus p plus q plus 1. So which is greater than the number of equation pq. So we need some additional restrictions to get a solution. So we write in that way, in order to get unique solutions, we impose p plus q plus 1 linearly additional restriction. That is summation alpha I from 1 to p, this is 0, summation j from 1 to q, beta j, this is 0, and gamma ij, j from 1 to q, 0 for all I from 1 to p, and I from 1 to p, gamma ij equal to 0 for all j from 1 to q. So this gives these additional restrictions, that is p plus q plus 1, gives the unique solutions of this unknown 1 plus p plus q plus p parameters. Okay. So under this restriction, actually it's better to write in that way. Okay. So under these restrictions, 1 becomes pq in mu equal to double summation I from 1 to p, j from 1 to q, k from 1 to m, yij, k, and this gives mu hat y naught naught bar, and y naught naught bar defined as 1 by pqa sum over I from 1 to p, j from 1 to q, k from 1 to n yi j k. Okay. Similarly, now from 2, now 2 becomes summation j from 1 to q, k from 1 to n yi j k, qm mu plus qm alpha. So then alpha I hat, which is equal to qm 1 by qm j from 1 to q, k from 1 to m yi j k minus mu hat, which gives yi not bar minus y not bar, where yi not bar is equal to 1 by qm sum over j from 1 to q, k from 1 to m yi j. Similarly, beta j hat is equal to y naught j naught bar minus y naught bar, where y naught bar, y naught j naught bar equal to 1 by pm sum over I from 1 to p, j from k from 1 to m yi j k, and gamma ij hat is equal to yi j naught bar minus yi naught bar minus y naught j naught bar plus y naught bar, where yi j naught bar is equal to 1 by m sum over k from 1 to m yi j k. Okay. So now the hypothesis defined, or where we want to test that means all alpha is equal to 0, all beta j is equal to 0, and all gamma I is equal to 0. So write this as the hypothesis that we usually wish to test is a all alpha equal to 0, is B all beta j equal to 0, HAV all gamma ij equal to 0. Now we write Yijk minus mu alpha I beta j minus gamma ij. So it can be written as Yijk minus mu hat minus alpha I hat beta j hat minus gamma ij hat plus mu hat minus mu alpha I hat minus alpha I plus beta j hat minus beta j plus gamma ij hat minus gamma ij. Now squaring and summing over ijk, we find that the cross product term vanish because of the side condition. Sorry, sorry. That is summation alpha I equal to alpha I hat equal to 0, summation beta j hat equal to 0, summation gamma ij equal to summation gamma ij hat equal to 0. These are the side conditions. We already discussed this in our previous class for all I and summation gamma ij, that is summation over j, summation over I gamma ij hat is 0 for all j. Sorry, for all j. Then we get capital L, which is equal to sum over I from 1 to P, j from 1 to Q, k from 1 to n, Yijk minus mu hat minus alpha I hat minus beta j hat minus gamma ij hat whole square plus pqm mu hat minus mu whole square qm sum over I from 1 to p alpha I hat minus alpha I whole square pm summation j from 1 to q beta j hat minus beta j whole square plus in I from 1 to p j from 1 to q gamma ij hat minus gamma ij whole square. Under this model omega, the minimum value of L is denoted by omega, which is equal to sum over I from 1 to t, j from 1 to q, k from 1 to n, yi j k minus mu hat alpha I hat minus beta j hat minus gamma I j hat whole square. And this is attained when mu equal to mu hat, alpha equal to alpha I hat, beta j equal to beta j hat, gamma ij equal to gamma ij hat. Okay. Under HA, that means all alpha equal to 0, then L become L omega plus, that means all alpha equal to 0. So this should be Qm sum over I from 1 to p alpha I hat square, because all alpha equal to 0, plus Pm j from 1 to q beta j hat minus beta j square plus m into I from 1 to p j from 1 to q gamma ij hat minus gamma ij square. This is again obviously minimized by the values mu equal to mu hat, beta j equal to beta j hat, gamma ij equal to gamma ij hat. And the minimum value of L under HA is denoted by HA, because consider under HA intersection omega, that is our model, which is equal to L omega plus this term Qm plus I from 1 to p alpha I hat square. And sum of square due to error, so this implies sum of square due to error, I denote it by sum of square due to HA, that is we denoted by sum of square due to factor A, which is nothing but a LHA intersection omega minus L omega. Hence, this is equal to QM sum over I from 1 to P alpha I hat square. Similarly, SSB or SS due to HB, which is PM sum over J from 1 to Q beta J hat square, and SSAB sum of square due to interaction, or SSHAB, this is M into sum over I from 1 to P J from 1 to Q gamma I J hat square. Therefore, we note that Yij k minus mu hat, this is equal to Yij k minus mu hat minus alpha hat minus beta j hat minus gamma ij hat plus alpha hat beta j hat plus gamma ij hat. So this is called orthogonal splitting. So this is an orthogonal splitting. That is, the components are orthogonal. Therefore, summation I j k Yij minus mu hat whole square, this is equal to summation I j k Yij minus mu hat minus alpha I hat minus beta j hat gamma ij hat whole square plus Qm sum over I from 1 sum over I alpha I hat square plus Pm sum over beta j hat square plus sum over I j gamma I j hat square. So this is simply as, this means a sum of square due to total SST equal to, this is called SSE sum of square due to error, SSA plus SSB plus SS due to interaction, SSA. Okay, so This is it. This is the orthogonal splitting of total SS. Therefore, SS E, SS A, SS B, SS AB are independently distributed due to Cochrane's theorem. Now, if you replace here the estimate of mu hat, replace mu hat by y naught naught bar, alpha I hat by y I naught bar, minus y naught naught bar, beta j hat y naught j naught bar, minus y naught naught bar, and gamma I j hat by yij not hat not bar, minus yi not bar, minus y naught j naught bar, plus y naught bar. Then you get SSE is sum over ijk yi j k yi naught j bar whole square. SSA, this is QM sum over I yi naught bar minus y naught bar whole square. SSB PM sum over j y naught j naught bar minus y naught bar whole square. SSAB in sum over I j j naught bar minus yi naught bar yi naught bar minus y naught j naught bar plus y naught bar whole square, and SST, which is yij minus mu hat. Mu hat means y naught bar. So this is yijk minus y naught bar whole square. So now we consider the test criteria criterion and testing procedure. The degree of freedom, df, I denote this df, not degree, f for freedom. Degree of freedom of SSA is p minus 1, since we have one linear restriction. That is summation I from 1 to p alpha I hat equal to 0, and p minus 1 alpha I hat are linearly independent. Similarly, the degree of freedom of SSB is q minus 1, because we have one linear restriction, that is j from 1 to q beta j hat equal to 0, and q minus 1 beta j hats are linearly independent. So degrees of freedom of SSB is q minus 1, and degrees of freedom of SSAB is PQ minus P minus 1 plus Q minus 1 plus 1, which after simplification we get P minus 1 into Q minus 1, and the error degrees of freedom we can argue similar way, because here we have only this number of equations are independent. We already knew this thing. So the degrees of freedom of SSAB is this, and the degrees of freedom, because of orthogonal splitting of SSE, is this is the total degrees of freedom minus this is the degrees of freedom of SSA, this is for SSB, and this is for SSAB. Okay, so after simplification we get PQ m minus 1, which is the error degrees of, and this is positive because we consider more than one observation parcel, that means m should be greater than 1. Now, this is your homework portion. It can be shown that expectation MSA, first I consider MSA, which is sigma square plus MQ sum over alpha square by P minus 1. Please do it yourself. This is your homework, and you know I think you knew the definition. MSA is nothing but SSA by corresponding degrees of freedom, where it is P minus 1. So MSA is SSA by its degrees of freedom, that is P minus 1. Expectation MSB this is equal to sigma square plus MQ MP, sorry, sum over J beta J square by Q minus 1. Please do it yourself. This is another homework. And expectation MSAB, which is equal to sigma square plus m sum over I j gamma ij square by its degrees of freedom p minus 1 into p minus 1. This is your another homework. And expectation MAC, this is equal to sigma E square. So please do it this yourself and submit. So we see that MAC is an unbiased estimator of sigma E square. And note that MS expectation MS AB, this is equal to MS expectation MSE under H naught AB, sorry, HAB. HAB. And this is greater than expectation MAC when HAB is false. Similarly, so this means MAC is a validator for testing HAB. So hence the ratio FAB, which is equal to MSAB by MSC, will give the test for HAB. And note that here MS is a validator for testing HAB. We reject. So one thing you should note that when you consider two-way ANOVA more than one observation per cell, you should test interaction effect first. So you should test interaction effect first. So if it is not present, then proceed further. Otherwise, you stop. That means if FAB is significant, that means HAB rejected, then you should stop. Do not proceed further. If it is rejected, that means fail to reject, that means FAB is insignificant, then you proceed further. That is the steps which I going to talking about, which I going to discuss. Okay, so we reject HAB at level alpha, which is the level of significance, for level alpha if observed if is, I denote this ratio by FAB. So observed if FAB is greater than F alpha P minus 1 Q minus 1 PQ M minus 1. Otherwise, accepted. Where this F alpha PQ P minus 1 into Q minus 1 PQM minus 1 is a upper alpha percentile point of F distribution with P minus 1 into Q minus 1 PQ M minus 1 degrees of freedom. Okay. So I already mentioned this thing. If H naught HAB is rejected, then you should stop here. Otherwise, that means if HAB is accepted, or it is better to say if HAB failed to reject, in that case we proceed further. That means we write this as if HAB all gamma ij equal to 0 is accepted. That means there is no significant interaction effect present. The test for HA and HB can be performed as follows. We see that since HAB accepted, that means gamma is equal to 0, and then we see that expectation of MSB and MSA both greater than equal to sigma square, which is expectation of MSC. So MSAB is greater than equal to sigma square, and this is equality hold under HA. Similarly, equality hold here under HB. Therefore, MSC is a valid error for both these tests. Okay, so HA is rejected at level alpha if the observed F, I denote this by FA, since MSC here is a valid error. So if observed FA is MSA by MSE, should be greater than F alpha P minus 1 PQ M minus 1. So this is a upper alpha percentile point of F distribution with degrees of freedom P minus 1 PQ M minus 1. Okay, and otherwise accept it. Similarly, HB is rejected if the observed F implement this by a P, which is the ratio of MSB by MSE. This is greater than F alpha Q minus 1 PQ M minus 1, and otherwise we accept it. Now, if HA is rejected, then we know we perform post hoc test, and so here we can also perform a post hoc test. So now if HA is rejected, the problem is we can find the level of A with the help of t-test, which is responsible for this rejection. Here I discuss only t-test, but I already discussed this issue, that is the type 1 error for family-wise type 1 error. If we consider only t-test, then type 1 error may be exceed alpha. So in that case, we need Bonferroni corrections. So here you can implement it. You can apply Bonferroni correction, and there are other some post hoc tests. For example, 2K test, FS test, etc. You can learn this in your post graduation class. For time being, I just discuss only t-test. Okay, so we can find the level with the help of t-test, and let I define L sum over I from 1 to P Ci alpha. If L is a contrast, then it should be 0. Sum over Ci equal to 0. You knew this thing from linear model class. Is a contrast of among alphas the contrast L admits unbiased estimators L hat, which is sum over Ci alpha I hat, and we know alpha I hat is yi not bar minus y not bar. So this is equal to sum over I Ci yi not bar minus y not bar, and this is simply sum over Ci yi not bar, because sum over Ci equal to 0 and y not bar is a constant. So this is simply as sum over I from 1 to P Ci yi not bar, and it is a linear function of independent yijk's, where yijk's follows normal distribution. So L hat follow normal distribution with mean expectation of L hat sum over I from 1 sum over I Ci expectation yi not bar. So this is equal to simply zero, and sorry, this is equal to, this should be mu. Okay, we write all this thing. So I denote this by capital L. So because if you compute all these things, so this should be Ci alpha. You can check. Okay, so which is L naught under H naught. I denote this by L naught. Okay, for timing I write this as sum over I Ci capital alpha. Okay, and variance of L hat, this is equal to sum over I Ci squared sigma E square. Okay, so since sigma square is unknown, now we want to test H naught sum over Ci alpha, which I denoted by capital L, equal to L naught. Then under H naught, L hat follow normal distribution with mean L naught and variance sigma square sum over I Ci square. Okay, since sigma square is unknown, so our test statistics which is P L hat minus L naught by root over, because sigma hat is square estimated by MSC, into sum over I Ci square. Under H naught, this follows P distribution of degrees of freedom. Degrees of freedom is PQ m minus 1, which is the error degrees of freedom. Okay, under H. Please check. This is your another homework. Okay, so I think there is a error. This should be divided by QM. Okay, please check. So this should be divided by QM. Okay, so this is QM. So this is the test statistics for testing H naught L equal to L naught versus H1 L naught equal to L naught. Can use this test statistics, and we reject H naught if at level alpha, if mod t, absolute value of t greater than t alpha by 2, PQ m minus 1. P alpha by 2 PQ m minus 1 is a upper alpha by 2 percentile points of T distribution with PQ m minus 1 degrees of freedom. Otherwise, we accept. Remark: it is important to note that the least square estimators mu hat, alpha I hat, beta j hat, gamma I j hat are unbiased, and in fact loose, because using Gauss-Markov theorem can say that these are the two unbiased estimators of mu alpha I, beta j, gamma I j respectively. Under under the restriction sum over alpha I over I equal to 0, sum over beta j and gamma I j equal to 0 for all j, and sum over gamma I j equal to 0 for over j for all I. If the restrictions are not satisfied, then yi not bar, this is equal to mu plus alpha I plus 1 by q. This is from normal equation. Just back to the normal equation and see that this is equal to beta j plus 1 by q sum over j ei not bar. So otherwise, just take consider the model, and from this model you can get this thing also. Okay? So and y not bar, this is equal to mu plus 1 by p sum over alpha I over I 1 by q sum over beta j over j plus 1 by pq sum over I j gamma I j plus E naught naught, and expectation y naught bar minus y naught bar, yi naught bar minus y naught bar, this is equal to alpha I minus alpha bar naught minus plus gamma I naught bar minus gamma naught bar, which is not equal to alpha I, where alpha naught bar, this is defined as 1 by p sum over alpha I, gamma I naught bar, this is equal to 1 by q sum over gamma I j over j gamma naught bar, This is equal to 1 by PQ sum over Ij gamma Ij. Similarly, we can check expectation of beta j hat. This is again not equal to beta j. Expectation gamma Ij hat. This is again not equal to gamma Ij. So if you consider this restriction, then these are the unbiased estimator. Otherwise, these are not unbiased estimator. Under this restriction, these are the, that means alpha I, beta j, gamma ij are unbiased estimator. Otherwise, they are not unbiased estimator. So we can conclude this. Similarly, mu hat, beta j hat, gamma ij hat are not unbiased if the restriction are not satisfied. Now consider the Anova table. For 2A classification with m observation per se. And first column is source of variation. Second column is degrees of freedom. Third is SA, sum of squares. Fourth is MS, mean sum of square. Fifth, F ratio. This is between level of A between labels of A, degrees of freedom P minus 1, SSA. Just write the expressions of SSA here. Okay, I already wrote this thing, just put it here. This is between labels of P whose degrees of freedom Q minus 1 and SSB. Just write the expression of SSB. Interaction AB whose degrees of freedom P minus 1, Q minus 1, SSAB. Just write the expression here. Error whose degrees of freedom PQM minus 1, SSE. Just write the expression of, just do it. Expression of SSE. Total the degrees of freedom is PQ M minus 1, SST, double summation, triple summation IJK, YIJK minus Y not bar whole square. MSA is SSA by P minus 1. MSB is SSB by Q minus 1. MSAB is SSAB by P minus 1, Q minus 1. MSA is SSE by PQ, that means corresponding degrees of freedom, PQ M minus 1. And F ratio, FA, which is MSA by MSC, FB, which is MSB by MSC, FAB, which is MSAB by MSC. Okay, so this is all about two-way classification with M observation. M means more than one observation per cell, fixed effect model. So have you any question? Follow me. Please tell me, or anybody who watching this video, please, if you have any question, please tell me. So next day, that is the Monday, next week actually, Monday, same time we will meet again and consider some practical example and show the computational process. Okay, the next class. So have you any queries? Please tell me, otherwise I end this stream. Thank you for watching this video. Thank you, Sudipta. So next day we will discuss practical example on the considering two-way Anova, one observation per cell and more than one observation per cell, both cases, and show the computational process. Okay, thank you till then, and thank you for watching this video.